All right. Welcome everybody to our Applied Math and Statistics Colloquium. I'm Paul Constantine. I'm an assistant professor in the AMS department. We're very excited to have Professor Randall LeVeque with us to give the colloquium. But we're going to start like we usually do with our world-famous AMS Colloquium correspondence. Izzy's not here today, but Jessica Daters will take it. Yeah?
Yeah.
All right. And so we'll do this.
Is there a clicker?
That. Yeah.
Okay. Hi everyone.
Hi.
Welcome back. So we're going to talk a little bit about just some cool math that's been in the news, and then Izzy and I recorded a segment of our new talk show to watch after that. I'm really excited about it. I hope you're also very excited about it. So we're going to start off by talking about how some researchers are using social media to model the spread of diseases. So as you may or may not know, back in August there was a mumps outbreak in Arkansas. So it started with about 7 cases in August of 2016, but then we don't really know how it spread. So they actually didn't keep records of how the disease spread, which is kind of a common trend through just trying to collect data. It's often really hard to get good data, especially dealing with diseases. So what this research group did is they actually used social media information to determine how the disease was spreading. And so they used the Health Map digital surveillance system. It collects social media reports and news about public health issues and turns them into data. Some interesting ethical questions tumbled up in that, but they were able to put this together where they estimated that by March 15th, which is just 9 days ago, there was almost 3,000 cases of the mumps in Arkansas. So this brings up an interesting question about vaccination, because mumps is an extremely contagious disease, and actually about 10% of people who are vaccinated are still susceptible to the disease. And so they estimate that you need about 96% of your population to be vaccinated in order to achieve herd immunity. And so what they were able to find through their data collection is that only about 70 to 80% of the population in Arkansas is vaccinated. And that's why we saw such a big growth in this. And so it of course drives home the importance of vaccination. I don't need to, anyways. But it also raises an interesting question of the use of social media and this digital data that we have about all of us in science. So I think it's interesting to kind of ponder the ethical implications of using social media to collect data to model diseases or whatever it is that you're modeling with it. So with that, we are going to talk a little bit about Dr. Deb Carney. So she is a mathematician in the AMS department, and we have our first installment of our talk show.
Of the Colloquium series. Today we are so excited. Our guest for the evening is going to be Dr. Deb Carney. If you could help us welcome her. Really an honor. Thank you so much for joining us here today. Thank you for having us. So we hear that you're a pretty influential figure in the math department, and you even had one of the math clubs. So can you tell us a little bit about your work with SIAM?
Sure, Society for Women in Math is just so well known for being the best club on campus, and we know that a lot of that is because of you. So we'd love to hear about that.
Sure. So I started SIAM with Becky Swanson, also a member of the department, and we started, it's our first year here. We felt like we both had benefited from mentoring groups when we've been undergraduates and graduate students, and it seemed like it was missing here in office. So that's how I got started. We're playing alumni, we kind of tell our history, we tell our stories, we share the tips and hints and things like that. And we thought that would be helpful.
Yeah. So that's something that we're all really proud of at AMS being incredible. And so how did you come to mind?
So literal way it came to mind was my husband showed me the job. And so we were both working at the University of Denver, and he's also a math professor. And he had something he started showing me that. He said, I think that really fits you. And so that kind of made me feel it was really awesome. So I like that. And it's really that a perfect fit from
In addition to all of the work that you do for these courses, what do you enjoy doing outside of this place?
So when I can find time, I love spending time with my family. I have 2 kids. They are one is 16, and he's 11. So lots of activities around the kids. Right now, we try to get outside. We like to go camping or that one. I try to exercise. I'm trying to take back care of myself. Because that's more you love that. There's a lot of things.
Like if you could have like one huge impact on something or change one thing, what would that be? What would that be?
So the change would be if I could just have more hours a day. It would be good enough. But as far as impact, I guess I feel like, and that's why I do what I do, that's why I love my job, so we can have different lives and students, however that means, they would find that, that's what I love.
And would you say that that's the biggest accomplishment?
Yeah, I mean, that's kind of day-to-day, that was what's keeping me going. I'm pretty proud to finish my Ph.D. There were times where I thought, maybe I should quit, this is not for me, but I haven't really that accepted it, and that really, I wouldn't be where I am today.
Well, you're not that you do too. I mean, with that, so when you're going through like things that are challenging and accomplishments, you always gain advice and you listen from it, and then you advice and listen on that, and you get to like someone what we're doing.
Yeah, you won't be perfect. That's my lesson we learn. And it's okay to stumble and fall, but you can really learn things. And those lessons, I think that is one of the biggest things. And all, whether it's everything. And I think, in mathematics, sometimes it is tricky. I think I sometimes thought it was the first that's kind of the way it's presented, but then finally figuring out people actually stumble and struggle and pieces, and it's, that's a good proof. You just didn't do that proof, or she didn't just do that proof right there. So, you don't always kind of see that backstory. So just kind of writing that for yourself as struggle with your phone.
Thank you.
Well, thank you so much for joining us. We have a wonderful swim mug to give to you as a thank you for your time with us.
Lovely. I would love to come back on your show. Right?
Well, thank you so much. You're welcome. And that's all, folks.
Good job. You can catch their cable access show on Colorado 746, actually. But wouldn't that be funny? Okay. And with that, I am pleased to welcome Professor Randy LeVeque. Randy, we have a gift for you. So that's for you. It was right under your feet the whole time. You didn't even know it. And you could join me up here at these stools. I've got questions to ask you. So, many of you are new to our colloquium, so just to let you know, in lieu of the traditional introduction, I usually interview the speaker for a couple minutes. And I've given Randy the questions ahead of time. This is not gotcha journalism, no CNN drama or anything like that. So Randy, thank you for visiting us at School of Mines for our colloquium.
My pleasure.
You are the Boeing Professor of Applied Math at University of Washington. You've been there since about 1985. You've held several visiting positions around the world. You're a fellow of both SIAM and AMS, the real AMS, not Applied Math and Statistics, but American Mathematical Society. And you were recently, well, you were elected to the SIAM Board of Trustees 3 years ago?
I guess.
Okay,
Yeah.
cool. So according to your CV, you've written 4 books, 78 journal papers, and many other academic writings. Which one is your favorite and why?
So that was a good question, even though I had it in advance. I don't think it's easy to say exactly. I mean, I've always enjoyed writing about conservation laws and numerical methods, and so my book on finite volume methods is one I kind of keep adding new examples as we're developing more software and keep working on that. But I've always kind of enjoyed papers where we've had a chance to either identify some new phenomenon or come up with a simple example to explain some phenomenon. I think those are my favorite kind of papers.
So which one would you point us to?
Well, so for example, we had a paper on nonlinear hyperbolic waves in layered media, where it's all hyperbolic, so you just have waves propagating, but because of the reflections at the interfaces, you get a sort of effective dispersive behavior. And then that combined with the nonlinearity gives you solitary waves of a sort that sort of hadn't been seen before, at least as far as we know. So that was kind of fun
Cool.
to look at.
So, well, speaking of your books, you're well known in our department as the author of the Math 408 textbook, Finite Difference Methods for Ordinary Partial Differential Equations. What led you to write that book, or do you have any interesting stories about it?
Well, I guess what led me to write it was having taught that class over and over again for 15 or 20 years, and every time I would write a new version of the class notes, and eventually I decided I'd done enough of that and it was time to just publish it so I could move on to other things. Yeah. But I've always sort of enjoyed writing class notes for classes I teach and then revising them as I go along.
Okay. And well, thank you for doing that, because now I don't have to. So this is a special USGS AMS Colloquium. Welcome, USGS people. For your research, what is the ideal balance between algorithm development analysis and applications?
I think that varies a lot. It's kind of varied over my career. I think when I started out, I was mostly interested in exploring numerical methods, proving convergence theorems, really understanding the methods. Then I got more interested in software development, and then started working more and more with people on specific applications, and in particular, for the last 10 or 12 years, been working a lot on sort of geophysical flow applications, and it's been a lot of fun just to kind of work with people who are experts in totally different areas. It's kind of one of the fun things about applied math in general. I think you get to go out and dabble in lots of fields, and the same equations come up so many different places.
Yeah. Where do you think the greatest impact is? Do you think it's more in the applications or more in the analysis?
It's hard to say. I mean, I feel like recently we've had impact in actually looking at tsunami modeling and having a chance to work with State of Washington Emergency Management Division and developing new inundation maps and evacuation maps and doing some work that really impacts people. So for me anyway, that's been very satisfying, fun.
Well, thanks for keeping our Pacific Northwest safe. So what sorts of things do you do outside of applied and computational math?
Like to go out hiking, camping, skiing, like to come to Colorado. We have a cabin, as you know, up near Netherlands, so got to engage in the lunch discussion about frozen dead guy days up there, and learned some new history about that I didn't know. So, but we like to hike and camp. And
cool. All right. Well, that's all for my questions. So thank you very much for joining us. I'll notice the setting for our interview was right outside the quad at Stanford, which is where you got your degree. And so we'll give you this and give you this.
Is that the pointer?
Yep.
Okay.
And Randy LeVeque.
All right. Well, thank you, Paul. This is, I think, the most interview-heavy colloquium I've ever been involved in, but I think it's a really interesting system. I should point out that at the University of Washington, there is a mumps outbreak going on right now, so I hopefully didn't bring that to you as well. But, I will try to keep this fairly brief, so I'm not going to be able to talk about all of the various aspects of what we've been looking at with tsunami modeling and whatnot. But I thought I would focus on how we're looking at generating random earthquakes that can be used as part of a probabilistic hazard assessment for tsunamis. So this is work I've been doing with a number of people who've been working with us at the University of Washington and elsewhere. I have here a figure that sort of shows the Cascadia subduction zone, which is offshore the coast of California down here all the way up to British Columbia, and a few sort of eigenmodes of that subduction zone, which I'll talk about later in the talk. But just to set the stage, if you're not sort of aware of the geology of the Pacific Northwest, we have a subduction zone that runs along the coast, which is active. For a long time, it wasn't really known whether it was active. It was only, I think, in the 1980s or so that they kind of figured out that this is a very active fault that does have major magnitude 9 earthquakes on average every 500 years or so. But the last one was in 1700, and so there hasn't been a lot of awareness of that locally until fairly recently. They now know from records along the coast of Washington and correlating with records in Japan, where there's a lot of history of mapping tsunamis that have come in here, that the last big one was on January 26th, 1700. And by looking at deposits, the sort of sand that's brought on shore by tsunamis and then gets buried by soil and then covered up with new layers of sand over the years. In some places on the coast, they can dig down and find like 17 layers over the last 10,000 years or so. And so they can sort of date how often these occur. It's fairly random, though, so we don't really know when the next one will be, but there's a lot of interest now in doing a better job of preparing on the coast for potential big earthquakes and tsunamis. So one thing we've been involved in the last couple of years is using the tsunami modeling software, which I won't really talk about at all, but we have a sort of shallow water equation with adaptive mesh refinement, finite volume code that solves for the propagation of a tsunami and the inundation onshore. We've been trying recently to use that in the context of probabilistic hazard assessment. So we've had a couple of projects now funded by FEMA to look at developing techniques for doing probabilistic hazard assessment. So this is Crescent City, California, which is up near the Oregon border, right about here. Offshore, there's a Mendocino Ridge that sort of acts as a waveguide and tends to focus some of the tsunami energy coming in here. And then because of the shape of the coastline and the continental shelf and the harbor, this tends to be hard hit by tsunamis coming from anywhere in the Pacific. So the downtown Crescent City, there's actually a park on the waterfront here, which used to be part of downtown until the 1964 Alaska earthquake, which went several blocks inland and destroyed much of Crescent City. And if there's a magnitude 9 offshore, then there'll be, of course, very severe flooding here. But even from other events like the 2011 Tohoku event in Japan, there was quite a bit of damage in this boat harbor, for example. So this was the community that was chosen as sort of a test bed for some of the probabilistic methods that we've been looking at. So this is a sort of standard tsunami evacuation map, which just shows a region of danger. This is the harbor down here, and then this is the downtown, and all of the sort of yellowish region here is the evacuation zone. But that doesn't really differentiate between a big tsunami from right offshore and one coming from across the ocean. So people are starting to look at ways of developing a more probabilistic hazard map that would say some areas are more likely to flood than others. In particular, FEMA is charged with creating things like 100-year flood maps and 500-year flood maps for setting insurance rates and things like that. So they've been struggling with how do we do this for tsunamis. So this shows the results of 4 different tsunami simulations in Crescent City from 4 different earthquakes. Again, this is sort of the harbor here and the downtown area here. This is, I guess this one here is actually a model of the 1964 Alaska earthquake, something like that did flood much of the downtown area and go up here in the Elk River Valley. This is the Tohoku event in 2011, but this was run at high tide. And luckily that tsunami came in at low tide, so there actually wasn't much flooding at all onshore, although there was a lot of damage in the harbor. This is another hypothetical Alaska event, and this is a Cascadia event, something that's right offshore, which you can see has considerably more flooding. And there's some events that give even much more flooding than that, potentially. So the idea is to take a lot of hypothetical earthquakes, do a tsunami simulation for each, and then combine them into some sort of hazard map based on the probability of each of the realizations you're looking at. Or ideally, rather than just having a finite discrete set of realizations, having some probability distribution of possible future earthquakes and come up from that with some sort of a probabilistic map of the hazard. So this might be sort of a probability 0.01 per year probability, so that would be like a 100-year flood map of what region might flood. And this was what was actually calculated using 15 different hypothetical Cascadia events plus another 17 or so events from around the Pacific Rim, and with some assumed probabilities for each, and then doing each simulation and combining the results. So that would be like the 100-year flood map. If we look at a 500-year flood map or annual probability 0.002, then there's a larger region that floods according to the model that we put together. Of course, there's other regions here that stay dry in this 500-year flood map, but could potentially flood in a more severe event, maybe with lower probability. So one thing we've struggled with lately is how do you best present this kind of probabilistic result in a way that people can understand and actually use, either emergency managers or the public ultimately. And one thing about a 500-year flood map in particular, if you're looking at Cascadia, I said it has a return time of about 500 years. So depending on exactly how you set that probability, you can get a very different looking 500-year flood map if you're only looking at that one particular probability. So you may want to have a much wider range of probabilities that you consider. Or another thing we've looked at is sort of turning it around, and instead of fixing the probability and looking at what's the expected depth of flooding. So this is in meters over here. So this is the depth of flooding that you expect to be exceeded with that annual probability. Instead, you could fix a level of flooding and ask what's the probability at each point, and then make a color contour map of that probability. So if we ask what's the probability of getting any flooding at all, depth greater than 0 meters, then we see there's a much bigger region that could potentially flood, but with probabilities that are much smaller than 0.002. Well, this is sort of the wet tennis shoes level of flooding. If you want to set the depth somewhat higher, you say, well, it's not really dangerous unless it's maybe half a meter, then you can set that level and look at what's the probability of flooding for that particular depth. Or if we go up to 1 meter or 2 meter, you get different flood maps. So one thing we've been looking at, as I said, is sort of figuring out how can we best present this sort of information. I just wanted to mention briefly a couple of projects that are going on at the UW. We had a workshop on exactly this topic of communicating hazard and risks at our eScience Institute a year and a half ago or so. The eScience Institute is our sort of data science institute on campus, but there's a lot of involvement from many different departments around campus. The M9 project stands for Magnitude 9, Cascadia Earthquakes. This is funded by the NSF Hazard Seas program. It's a very interdisciplinary grant that involves people in earth sciences, civil engineering, public affairs, College of Built Environments, and various other groups that are getting together and in particular trying to understand sort of all aspects of a magnitude 9 earthquake, the resulting tsunami, landslides as well, and also some of the issues about probabilistic hazard assessment and communicating risks. So probabilistic tsunami hazard assessment, there's been a lot of work done in the past, not as much as in probabilistic seismic hazard assessment, which I know a number of people here work on in particular. But the tsunami hazard assessment probabilistic side has been sort of more recent developments and based to some extent on what's been done for seismic hazard assessment. But the issues are somewhat different in the tsunami case. And the sources of uncertainty that we have to worry about, the biggest one, of course, is the earthquake source. Where might the earthquake come from? And for distant earthquakes, often just sort of the location, the magnitude, and a return time or an annual probability is maybe enough, and you don't have to worry too much about the details of how the slip actually happened. But when you're looking at a nearshore event, like Cascadia in the case of the West Coast, then the details of the slip pattern, exactly how the earthquake slips at different points on the fault, can make a big difference in how big the tsunami is. And so what we've been looking at is ways of sort of generating random slip patterns that have a reasonable probability distribution or a specified probability distribution. We also worry quite a bit about things like the tides, because as I mentioned, the tide or a tsunami coming in at high tide will potentially do much more damage than if the same tsunami comes in at low tide. So I've been working with Lois Adams, who's also here with me, and others at UW on sort of how do we look at incorporating the tidal pattern at a particular location like Crescent City together with the pattern of waves that come in from various tsunamis and sort of build the probability of being at a different tide stage into the probabilistic analysis of flooding depth. And then there's various other uncertainties I won't really talk about at all, but they're important. How do you model the bottom friction or the effect of vegetation and structures? All the uncertainties in the mathematical model and the fact that we're using an approximation and then applying a numerical method to approximate those shallow water equations. But for the purposes of this talk, the big one is the earthquake source. So this is just an example of what we call a hazard curve at one particular point. So this is kind of a snapshot of Crescent City here. There's one point in the river valley there. And what's shown here is for different exceedance levels or different depths of flooding, what's the expected annual probability. So this is what we hope comes out of our modeling, is a hazard curve like this, but not just at one point, but rather at a dense set of points every 10 meters or so, covering the entire community. And then from those, you can do contour plots either of depth for a fixed probability or probability for a fixed depth. And so these curves are what we sort of build up by doing mini tsunami simulations and look at what's the maximum depth you see at each point, and then combine that with the probability of that particular event and with all of the other events. And so this top green curve is sort of the overall hazard curve at this particular point. And then the blue and red are sort of, if you split it up and only look at the far field sources, the ones coming from across the ocean, these red ones, those are the ones that are more likely to come. So at higher probability, those are the ones you see, but they have a lower level of exceedance or a lower depth of flooding. The blue ones are if we only look at the Cascadia sources, which have a probability of 0.002 or less. So they start here, but they're the ones that give the much greater flooding. So that's just sort of a flavor of what it is we're trying to get out of our modeling. And so as always, we have sort of different types of uncertainty in the problem in looking at this, the aleatoric uncertainties, the epistemic uncertainties. So the epistemic uncertainties in this case would be what's the right probability distribution of future earthquakes. And so that's really sort of a geophysical problem. We need help from the seismologists to answer the question of how can we best describe a reasonable, physically meaningful probability distribution for future earthquakes. Of course, that can never really be known, but at least we want to get something that seems reasonable based on best that's known about this particular subduction zone. And then there's the mathematical problem of if we were given a probability distribution and our numerical model for modeling tsunamis, how can we most effectively sample that distribution and without having to do tens of thousands of simulations, come up with estimates of these probability curves. If we only had a few finite number of potential earthquakes with discrete probabilities, then we could just run them all. But if we have a whole probability distribution, we have to sample it, and it's typically in a high-dimensional space. So that's sort of the question that we've been looking at is more on the mathematical side of, given some probability distribution, how do we efficiently sample it if it's in a high-dimensional space? Yeah, so there are various things you can look at. Again, we've looked a little bit at proxy models that are much cheaper to compute than the full tsunami simulation. There are other ways in which you can maybe come up with some reduced order model or surrogate model that's cheaper to run than the full tsunami simulation, but that gives a good result, often based on doing a relatively small number of fine grid simulations with the full model and then using that to build up these sort of surrogates. And then there are various techniques that have been developed for sampling this high dimensional space, which I won't go into in too much detail here. So for the first project we did on Crescent City, we were actually given a discrete set of 15 Cascadia events, as I mentioned. So this is sort of the uplift or subsidence of the seafloor along the coast for 3 of these 15 events. And we got these from some earlier work that had been done on probabilistic tsunami hazard assessment down in Oregon. And so we took those as given, and they had been developed using a logic tree approach where they split the Cascadia subduction zone possible earthquakes up into 5 classes with these sort of t-shirt sizes from small to extra, extra large. And then within each size, they had 3 different types of earthquake depending on whether the rupture was deep on the subducting fault plane or shallow closer to the surface, or the other case was if there were splay faults, which are additional faults that go right up to the surface from the subduction zone fault, which can cause much more uplift right at the surface and a bigger tsunami. And so for each of these, they had 3 different possibilities, and then they assigned some weights to those possibilities. And so there were a total of 15 different scenarios with 15 weights that added up to 1. And so we took those as being sort of conditional probabilities. Assuming this event happens with overall probability 1 over 500, say, then these are the conditional probabilities of these 15 events. And here they are in more detail. But what we've been looking at more recently is, can we generate our own realizations rather than just taking a small number, because there's really a huge variety of possible slip patterns one could have. This is an inversion for slip from the 2010 event off the coast of Chile. So the subduction zone fault is split up into subfaults, and the colors here represent the amount of slip on each of those subfaults. This is from a seismic inversion. And this is the resulting seafloor deformation. So when you have slip on this subducting fault that's deep under the earth, that causes, of course, seismic waves propagating out. But from the standpoint of the tsunami, we can often ignore those propagating seismic waves. And what we really care about is, how is the seafloor deformed? Because the seafloor deformation lifts up the water and creates the tsunami. And that tsunami is often generated on a much slower time scale than the seismic waves are propagating away. So if we know the final seafloor deformation, that's often used as the initial conditions for the tsunami. More recently, we've been doing some work on actually modeling the seismic waves and coupling that in with the water layer to see in more detail how the tsunami is actually coupled to the seismic waves. In particular, we've been looking at some earthquake early warning possibilities for Cascadia, where if you want to do sort of real-time tsunami warning for a near-field event, you really have to worry more about that coupling. But for the work we've done in the past, we've always used this assumption that from the slip, we can generate the seafloor deformation. And so there's a model that's often called the Okada model in tsunami modeling, which is basically a Green's function solution of an elastic half-space problem. So if you assume the Earth is an homogeneous half-space and you have a dislocation across some buried rectangle at some orientation, then that causes a steady state deformation of the surface. And there's a simple set of formulas for that. And then if you have many different subfaults, you just add those together. It's all linear, and so you can get a linear combination of the resulting uplift gives you the uplift or subsidence of the seafloor. This is the coast of Chile here in this case. So another important point to note is that you often have uplift offshore and subsidence onshore because of the direction in which things are slipping. But it can matter a lot if you're right on the coast. It matters a lot whether you have uplift or subsidence at that particular point, because again, the tsunami is going to be much worse if ground has dropped by 1 meter or 2 than if the ground went up by 1 meter or 2. So that comes into sort of the tsunami simulation as well.
Can you give a sense of scale about how long it would take? I'm not sure what the distances are here.
Yeah, so these are degrees, and a degree is about 110 kilometers. So this is like 400 kilometers. And so each subfault might rupture, the seismologist in the room can correct me, but might rupture with a rise time of something like 20 seconds or something, and then the rupture itself would maybe initiate at one point and spread out at a rate of something like 1 to 2 kilometers per second. So for this size, it might take 100 seconds, 200 seconds, something like that. For the Sumatra event in the Indian Ocean in 2004, that was a 1,100 kilometer long fault. It took about 10 minutes for that rupture to propagate from one end to the other. And Cascadia is sort of similar dimension, so it can take a long time for the rupture to propagate, and that's, again, that will potentially greatly affect how the tsunami is formed and how bad the effect is at different points on the coast as well.
I was thinking of the advice to run like hell.
So yeah, in terms of early warning, if you're on the coast and you feel a big earthquake, do exactly that and get to as high ground as you can as quickly as possible. But we're also interested in warning, like in Puget Sound, where it can take a couple of hours for the waves to get in there. On the coast, people only have maybe 30 or 40 minutes before the biggest waves arrive. But yeah, so if we want to generate sort of random slip patterns, then we could think of having all these subfaults and having a slip assigned to each one of them. If we have m subfaults, that would give us sort of a vector in an m-dimensional space. But the dimension grows rapidly. If we thought of all those as being sort of random slips and we could assign them all randomly, then we would have if we had, say, 180 subfaults, and we wanted to sample sort of a 180 dimensional space with 5 points in each dimension, well, we'd have something like 188 billion simulations we'd have to run in order to sample that space. Okay, so we're not going to do that, obviously. But luckily, we don't have to sample every subfault being random, because there's usually some correlation. If one subfault is slipping, then the nearby ones are typically slipping in a similar way. The farther away ones, less so. And so you can make some assumption that maybe there's an expected value of slip at each point, but there's also a standard deviation, but also there's a covariance that the expected value of the slip on one relative to the slip on another is given by some correlation, Cij times some standard deviations. And if you make that sort of assumption, then there are ways to generate random slip patterns that have that expected covariant structure. So one way to do it, if you have a rectangular fault in 2D, or if we go to just 1D and look at just, say, assigning slip on the down dip direction in a one-dimensional fault, one way that you can do it is with Fourier series. So if we thought of saying the slip was some linear combination of Fourier components with coefficients zk's, maybe some random coefficients, then the lower wave numbers give things that are smooth. Higher wave numbers give things that are more oscillatory. And so if you assume there's some correlation length, then that translates into some decay rate of the Fourier coefficients. And you can work out from an assumed correlation what the resulting decay in the Fourier series should be. And then you can pick random coefficients that decay at that rate and sort of generate random Fourier series that have the right sort of correlation properties. So you can choose then these z's to be independent random numbers with appropriate mean and standard deviation, and by forming the sum you get something that has sort of the right correlation structure. The idea of the Karhunen-Loeve expansion is to do something sort of similar, but it works on more general geometries. It doesn't have to be a rectangle, say, in 2D, where Fourier coefficients might be the most natural thing. So the idea of the KL expansion is to take the slip on subfault I and J and the correlation between those to make a big covariance matrix. So if you had an M subfaults, you'd have an M by M covariance matrix. And then if you compute the eigenvalues and eigenvectors of that matrix, it turns out you can describe the slip as the mean slip over all the different subfaults, plus a linear combination of eigenvectors, Vk, weighted by, again, independent random numbers with an additional scale factor that's the square root of the eigenvalue. And if things are highly correlated, then when you look at this covariance matrix, the eigenvalues decay rapidly. And if it were a rectangle, these would be essentially sort of Fourier modes. And the decay rate of these eigenvalues would sort of tell you the right decay rate for these components. And so you can choose the z's to actually be independent, normally distributed with mean 0 and variance 1. And then the eigenvalue sort of takes care of the decay properly. And I won't go into details in the math. I think we're going to be running late here. So, but if you're interested in this, you can sort of work out that if you make this assumption in terms of the eigenvalues and eigenvectors, that you can show that, in fact, the expected value of S minus mu times S minus mu transpose is exactly the covariance matrix that you started out with. Also, we often want the slip to be non-negative, so another trick you can play is to say instead of being sort of a Gaussian field, it should be a log normally distributed field, but with a desired covariance matrix. And you can do that by taking your desired matrix and computing from it this sort of Gaussian C hat G and a Gaussian mean, and then do the KL expansion as usual with those, but then exponentiate what comes out of that, and then you'll get something that's guaranteed to be non-negative, but still have the desired covariance, the covariance you specified to begin with. So if we look at this in 1D, so this is now looking at sort of a dipping fault plane, but we're just looking at kilometers in the down dip direction. This dashed line is a taper that you can also put in if you say that the slip should be going to 0 as you go further down towards the down dip edge. If you make that assumption, and then you also assume that there's a covariance that decays exponentially depending on the distance between two of the subfaults, then you get a covariance matrix whose eigenvectors are just the curves shown here as the colored curves. And they're sort of like Fourier modes. The k equals 0 curve is the one that only has a single maximum. The k equals 1 curve has 2 extreme points, and so on. So they're sort of like the Fourier modes, except they've also built in this taper function. And if you look at the eigenvalues, this is on a log scale, so they're decaying exponentially. Or they're decaying like 1 over k squared, I guess. In this case, it's a log-log scale. So for a one-dimensional problem, we could create a sort of a random slip pattern in 1D by doing this. And what you get is things that are shown on the left here. So this is just the mean slip if we just look at the taper. What I'm showing on the right is the resulting seafloor deformation after we apply this Okada model to a bunch of subfaults with the specified slips. We get some uplift over here, subsidence over here. Then what's shown here is something similar, but if we take 20 terms or only 3 terms in a KL expansion with some random coefficients. And again, as we add more terms, we're adding more highly oscillatory modes, and so the blue curve is more oscillatory. The red curve is with the same first 3 coefficients, but throwing away the rest of it. And so it's kind of a smoother approximation to it. It doesn't look like a very good approximation, but what's really important for tsunami modeling is that when we apply the Okada model to look at the seafloor deformation, the deformation we get from the 3-term expansion is actually pretty close to what you get from the full 20-term expansion. And that's because the sort of highly oscillatory modes on the fault plane, by the time they are influencing the sea floor, have been filtered out quite a bit. The small or high oscillations in slip on the fault plane get smoothed out in terms of the resulting seafloor deformation. So if all we care about is tsunami modeling, then we don't necessarily need to include these higher frequency modes at all. We can get an approximation with only a few terms. And the number of terms, remember, determines the dimension of the space that we're working in. If we're trying to sample the space of random earthquakes, it's much better to be in a 3-dimensional space than a 20-dimensional space.
Amen.
And this is just one other sample realization with different random coefficients, same magnitude roughly as before, about a magnitude 9 on this one-dimensional fault, with some assumed length in the other direction. And again, 20 terms and 3 terms don't look very similar here, but they look quite similar in terms of the seafloor deformation. But they look very different from this realization, even though they're both roughly the same magnitude earthquake, and they would give very different tsunamis, perhaps. And again, going to 2D, if we have a rectangular fault, you could use Fourier series, and that's been used a lot in PSHA and PTHA too. In particular, Mai and Baroza looked at a history of a bunch of different faults. They weren't looking at subduction zone faults, they were looking at other faults, but they sort of investigated different assumptions about the decay of the correlation, and they found that I think about a 40% length of the fault was a reasonable correlation length to use, and then use something like an exponential decay, or they had a few other possible correlation functions that they looked at. Graves and Patarka also used this idea and extended it also to sort of time-dependent ruptures. So again, finally going back to the Cascadia subduction zone, where we have this sort of shaped fault, we could split it up into a bunch of rectangles, build up a covariance matrix based on the number of subfaults that we split it up into, and then compute the eigenvectors of that big matrix. And if we plot those eigenvectors, what we get is things that look sort of like Fourier modes, but now shaped to the shape of this fault. And again, as you go up to higher modes, they become more oscillatory. We're not at all confident that this is a good approach really for specifying random slip on this long of a fault. This is something else we'd really love to get more input from seismologists on. Should we be sort of splitting it up into subpieces and doing something on different segments of it individually? But one thing we've recently been looking at is, again, going back to Crescent City, we've decided to sort of focus on some smaller events that were concentrated more near Crescent City, just down on the southern end of the fault. And so we've been applying this idea to kind of test out how well we can use this as a way to generate random earthquakes and how many terms we really need in these sort of expansions if we're going to use them for the context of tsunami modeling. So these are 5 different realizations when you use these modes and additional ones with, again, random coefficients weighted by the decaying eigenvalues. So again, the red areas are high slip, the dark blue is low slip. And what's shown below it is the resulting seafloor uplift or subsidence. Crescent City is sort of where this X is there. And then what's shown in the next row is the same realizations as in the top row, but keeping only 7 terms instead of all 60 terms. So they're sort of smoothed out versions of the top row. And then the resulting seafloor deformations from those smoothed out versions, which are, again, similar to the seafloor deformations you get from the full. But then we've tried to sort of quantify this more. If we only use 7 terms rather than 60 terms, and we generated not just 5 realizations, but 20,000 realizations, how well do we do in looking at things we care about for tsunamis? So this is just one example of what we've looked at that you can actually look at cheaply enough to do 20,000 realizations. We can't do that many tsunami simulations, but we can generate that many random earthquakes and apply the Okada model to them in fairly short order. So what we've looked at here is just 2 sort of quantities of interest that might be proxies for how bad a tsunami is. Eta max is sort of the maximum sea level out in the ocean, which agrees with the maximum seafloor deformation, how big the wave is at its biggest point at the time the tsunami is initiated. And the other axis is how much subsidence or uplift was there at Crescent City, which again affects how much flooding there's going to be at that point. And then this is sort of contours of a 2-dimensional probability density function determined empirically from taking 20,000 samples from that KL expansion using the full 60 terms. The slide shows sort of the marginal densities over each of them separately. And then the next slide is the same thing, but if we truncate each of those 20,000 realizations to only 7 terms instead of using all 60 terms, what's the probability density of resulting quantities of interest there? So if we go back and forth between them, they're fairly similar, even though we're working, or we'd only have a 7-dimensional space to sample if we wanted to sample this and now actually do tsunami simulations as opposed to a 60-dimensional space there. And there are ways to sort of more quantitatively compare 2 probability density functions and see how they agree. And you can look at how that varies as you increase the number of terms, and you see that they become more similar as you increase the number of terms. So I think we're about out of time, so I'll stop there. But if anyone's interested, there's a number of papers on my website. There's links to most the papers we've written, but also in most cases to the code and the data that goes along with it. We've been trying to do a good job recently of posting all the code either in GitHub or on Zenodo, which is a place at CERN where you can issue a DOI to any set of data and code. So we've been trying to do that regularly. If you're interested in the tsunami modeling aspect, there's a lot more information at geoclaw.org. And these are a few of the papers related to what we've been looking at most recently. So.
Questions for Randall?
Yeah, two quick ones. In terms of uplift or subsidence at Crescent City, that was predicting uplift, but is that what is seen in the paleo record here? Or?
Yeah, so that's actually one of the issues, and we don't claim that our model at the moment is is doing a good job of.
In reality, and that's something we've been talking to various seismologists about, how to kind of choose the parameters and what's the right geometry to use for the fault, and how should we taper it at the down dip edge and so on. Because yeah, all of these sort of show, well, Crescent City is kind of right on the hinge between where it's uplifting and subsiding, but a lot of our realizations show more uplift than we think is really seen there. Although I think the record on the coast around there is not as good as some places.
Good place, that's
Yeah,
right.
we talked to people at Humboldt State who've looked at that a lot.
And then to jump off that, you showed the Mali rupture, and you showed how there are two big distinct slip patches in that. And then you raised the question, should you start with uniform slip all the way along and build from there? And it seems like if you do take that approach, then you end up with patterns like this, where you do have sort of fairly uniform slip patches rather than too chopped up. And I'm just wondering if, and maybe Gavin jump in here, but what's a way to end up with more clumpiness in the slip before you go to all into a bunch of modes, just right off the beginning?
So if you want more sort of clumpiness, certainly if you sort of decrease the correlation length, which has the effect of making the eigenvalues decay more slowly, that means that more of the highly oscillatory modes will be important in the sum, and then you can get more sort of clumpy. Like you can see here, even just going from 60 terms to 2 terms, here it looks like there's sort of only one high slip area, whereas here you see there's really sort of 3 if you start adding in these more oscillatory modes. We haven't looked at ways of sort of trying to say, well, in this region there should be an asperity or something, or there's really a high slip patch concentrated in one particular area. We could maybe add that sort of thing on as well.
Randy, thanks, that was a great presentation. Following up on that, I was just wondering, Graves and Pitarca and the Martin Mai stuff, 2010, 2002 or 3 or something, they're mostly crustal earthquakes, and in addition to that, what we saw in 2011 was 50 meters of slip on the Tohoku in the shallow zone, and
Yeah.
I don't know whether using the coefficients that would derive from those patterns from Martin Mai and Graves would ever get something that's 3 or 4 sigma outside of the maximum slip, which just happened after these papers were done.
Right. Yeah, so that's another question. And I mean, you can if you assume, or if you go out far enough into the tail of the distribution. We actually are just finishing a paper, our final report for another FEMA project on source selection for Cascadia subduction zone, where we wanted to generate 400 realizations and then do fine grid simulations on all of them, and then see how could we sort of use some of the techniques we've been looking at for multi-resolution improvement to get the same hazard curves out of far fewer simulations. And so for that, we did actually go out like 4 standard deviations, and we purposely picked a lot that were kind of pretty far out in the distribution. And then we were getting some that had, 100 meters of slip. And we were again looking at the sort of southern patch of the Cascadia subduction zone. So if you go far enough out in the distribution, you can certainly get a huge slip. And those were still like magnitude 9 or so. But it's a good question, what's the right way to choose these parameters so that we get things that are really reasonable. Yeah, and again, there's the question, when you have this very long, the full length Cascadia subduction zone, is this at all a reasonable way to generate slip patterns over the entire subduction zone, or should you really be splitting it up into segments or doing something totally different?
Is the tsunami modeling problem linear enough that you could create Green's functions for each of the slip patches?
So out in the deep water, yes, and in fact that's one of the techniques that NOAA uses for the warning that's currently done. They have these dart buoys, which are covered pressure gauges on the ocean floor that measure a tsunami as it goes by, and they do a rapid inversion based on that to write the earthquake as a linear combination of unit sources. And then they just take linear combinations of pre-computed tsunami models over the entire ocean, and that gives a pretty good estimate of what's going on as the tsunami approaches shore. Because out in the deep ocean, where the water is 4,000 meters deep and the tsunami is less than a meter high, it is very linear. But once you get close to shore, it becomes highly nonlinear. So in terms of the real-time warning that they do, I think they use that to get sort of boundary conditions for
nonlinear simulation in the near field if they really want inundation. In our case, if we're doing sort of probabilistic hazard assessment where we want to generate maps of inundation, most of the work is in doing the inundation on grid on shore and running our tsunami model out in the ocean. We can use coarser grids because the wavelengths are long. So that part is really quick, but then when you need a 10-meter resolution grid over Crescent City or something, that's where it really bogs down. But that's where it's not linear, so you can't just take linear combinations. But we have been looking at, can we take linear combinations of some simulations and maybe do something more sophisticated using a single value decomposition to analyze those and write, at least get an approximation of what the inundation pattern is from some future. And I think there's tons of other ideas that could be used here. There's a huge number of techniques that are being used in uncertainty quantification.
Too many
other people
Yeah.
know. And there's also this whole field of machine learning where taking data that you have one place and trying to predict what's going on someplace else, you can ask as a machine learning sort of problem. So there's lots of other things we've started looking at.
Paul, last question?
What is slip? To me, I think of slip as a fault in that integrity, and it just means that it goes like this.
Right.
So
So when I say slip, what I mean is how many meters is it?
Why can't it be
relative to
negative? Why can't it be negative?
So the assumption is that the oceanic plate is subducting beneath the continental plate because it's heavier, denser material. So that's where you get these subduction zones. And so typically it's moving down slowly at a rate of like centimeter a year or something, and it's kind of pulling the continental plate with it because it's sticking, and then every now and then it slips. And so when it slips, the continental plate is moving up relative to the oceanic plate that's moving down.
So, I mean, is that a theorem that it does that? I mean,
I guess you can have...
It's kind of being built into the model, and I'm wondering if that's removing the possibility of negative slip.
Devin could probably say how often do you see negative slip on stuff.
You have to reverse plate tectonics.
Yeah, plate tectonics would be this.
And it slips. And so when it slips, the continental plate is moving up relative to the oceanic plate that's moving down.
So, I mean, is that a theorem that it does that? I mean,
I guess you can have...
It's kind of being built into the model, and I'm wondering if that's removing the possibility of negative slip.
Devin could probably say how often do you see negative slip on stuff.
You have to reverse plate tectonics.
Yeah, plate tectonics would be the theory. Observationally, we don't see it.
Great. Well, let's thank Randy. You guys know what's happening. So if you come to USGS, if you are